Welcome back to Book Club. And today I'm actually going to do three topics, both brief, and hopefully this is about the same length as all the rest of the videos. And they're all kind of related. Okay, so it's actually going to be curve fitting and Fourier analysis and interpolation. And they're all kind of related to the same thing. So a lot of this is I have some data. So let's talk about the first one, which is curve fitting. Okay, so you have some data that you've gathered, some sort of real world measurements. Okay. And you want to fit a curve through here. Now, you might look at these data points and say, no problem, I'm going to fit a straight line through this, and it'll look sort of like that. And so the goal here would be, what's the line? So, slope and intercept, if you will. But that's a straight line. You could fit all sorts of things through here. In fact, the really nasty version, not that I can recreate the same dots, but here's also a curve fit, which is through each one of these. That's a curve fit as well. Now you might call it interpolation, which will be, that's why this is the bookend. But curve fitting is actually, there's one version we can do it which is related to what we've done in inverting a matrix. And there's others that are very close to what we've done. So all of this ultimately comes from, I have some data points that I'm trying to deal with. Now, there's always jokes out there on the internet of like, what happens if you had a data point down here? You just throw it out because it screws up your data. So not to get into the world of data science or how do you validate that these are real data points or what's the uncertainty, nothing is actually, if you took a measurement, nothing's actually a point, it's actually some uncertainty based on your measurement apparatus, depending on the physics you're measuring. So not getting into any of that, let's just say you have these points and you're trying to put a curve through it, okay? And so the first thing to talk about is actually just the average, right? And so if you had a bunch of points, the average, which we'll call y bar, is just the sum of y divided by the total number of points. Okay, standard average definition. Okay, and then the spread, we actually will talk about the deviation. Okay, so sy, standard deviation of y, would be the sum of each ith point minus that average, okay, squared, and then divided by n minus 1. Now, you can go dig into and see why it's divided by n minus 1. You'll see the derivation there, but that's the definition. Okay, so this is going to then say, each one of these points, how far away. So if I sum up, draw a perpendicular line to each one of these points, if I sum up sort of the length of all of those perpendicular lines, I'm getting an idea of the spread. How far away are my data points from that? So that's the standard deviation. Now, there's a thing called the normal distribution, which is kind of this bell curve, which is saying, hey, I have a mean. That's my y average, and I have these sort of deviations around it. And there's some models for that, and that's, we have kind of standard distribution model that we fit into it. It's basically an exponential with kind of quadratic squared. So there's probably some standard language that you've heard from all of this, but the piece I actually want to land here, because you can kind of find all this stuff online, or it's pretty easy. The thing I want to land on is how do you actually calculate that? And then one of the reasons we will actually look at the squared is because of how it makes our life solve for it. So if we say what we want to do is to define the error as the sum of sort of each one of these components. So I'm going to take my the ith data point, and what I'm ultimately trying to do is I'm trying to find a line that looks like ax plus b, right? So if this is the x-axis, right? X-axis and y-axis. And so I'm trying to find a. A is unknown. I actually know x, and I know yi. And so really what we're trying to do here is it's the ith data point minus that line. So that's actually a0 plus a1x. Use a different configuration here. So a0 plus a1x. All right. And so it's the difference between that squared. Okay? And you're going to sum it up over all of your points. So we'll just say sum over capital N. Right, so that's the error. So what do we do if we're trying to minimize the error? This is a function of two variables, right? It's actually a function of a0 and a1. And so we can say we want to take the derivative of e with respect to a0 and set it to 0. And we take the derivative of e with respect to a1 and set it equal to 0. And solution to that will be the minimum. Okay, so if we do that, then we see this whole thing comes down, and you get a 2 times the sum of yi. Okay, I have to take the derivative minus a0 plus a1x. and then times the derivative of a0, kind of chain rule, that's it. And then here, same thing, the 2 comes down, sum yi. So the same format here, a0 plus a1x, but then this time it's a derivative of that, so you get an extra x in front of it. Okay, so we can actually solve this, and what you want to see here is that actually you can form a matrix, and then what you end up doing, if you do this out, and you kind of write the above equations out, you have n, so the total number of data points, the sum of all the x's, and then on this portion is the sum of all the x's, and this is sum of all xi prime. This is times a0, a1, and that's equal to the sum of all the y's, and this is the sum of all xi, yi multiplied together. So you're just taking these 2 lines and splitting it out. This is a 2 by 2 matrix, so it's a linear solve. Okay, so this is sort of quadratic, fitting a line and solving it by sort of the square of the error actually generates a linear matrix. That's one of the reasons it's tried and true. It's 2 by 2 matrix. You can actually solve for this directly, but of course you can put it in a computer. So this is a very simple method, and a couple things that I want to highlight that kind of out of this. One, if you want to fit a nonlinear curve through here, right, you're not actually going to land with a linear matrix like this. And so what you end up doing is you sort of solve for the kind of the variations. You do these partial differentiations by basically exploring. And so if you have a package like MATLAB or a package like Python, they all kind of have these features in there. So it's not hard to do, but just know that you're going to have the same tricks that we've seen sort of in the past, where some guesses actually may be computationally stiff. It may be hard to find the solution. Okay, that's the first one. The second one, if you ever heard the R² error talking about this, it's actually a normalized error. And so what it is you're actually taking the standard deviation for this, right? So you can come back and calculate the standard deviation by summing. You have your y average. It's your curve fit. So you're summing up all of this, all of the little lines, okay? And then what you're actually dividing by is the error if all I did was use the average. So on a line like this that's kind of going up and to the right, your average might be somewhere over here. So R², we always think of R² of 1 as being really good. Yeah, it is, because R² of 1 is effectively saying it's perfect. But really, if you have an R² of 0.7, it's hard to say it's bad, because it could just be that straight line is pretty horrible. But so just anyways, I've seen people fall down that trap before. In fact, I remember one researcher, I won't say the field name, but they were saying that in their experiments that they only get R² of 0.5. That was a very high correlation. And so just anyways, be careful out there with curve fits. Be careful what you choose. You can actually apply a lot of the whole causation versus causation. You can imply a whole lot of things by the shape of a curve that may not actually be true. There may be other reasons for the shape of the data. So just kind of caution that these are out there. Okay, and then sort of a related one, and that's why I'm kind of doing all these 3 things at once. If I have some sort of data set, signal, and it could be a sound wave or any of these different things that has frequency content. Okay, this function, I'll just say this is y as a function of x. It could be y as a function of time, however you want to say it. You can actually decompose this function into a whole bunch of sines and cosines. Okay, so this could be a sum for n equals 0 to some capital N, and I'll just write it like this: so a0 of sine nx plus b0 of cosine nx, or b sub n is what I'm saying. N equals 0 to capital N. Okay, so you can always fit sines and cosines through this. So if I was to look at this sort of really funny thing I did, maybe it's like some frequency like this plus a smaller wiggle like this. You can kind of keep stacking this up, and this is called Fourier analysis. All right. Also standard in every MATLAB package and every Python package. You're basically decomposing this, and you're actually converting it. When you sit back, what you're actually doing is converting from sort of spatial space, like x versus y, into a frequency space. And so you're going to have some amount of amplitude at a certain frequency. Okay, so very, very useful for lots of, again, audio signals. You can think of it naturally. We use it a lot in turbulence research, like what are the frequencies of these eddies. And so not only is this a powerful method for, there's actually ways where you can use sines and cosines to solve, especially if it's periodic problems. Fourier analysis is very powerful for kind of this power spectral analysis. Now, the reason I want to highlight it here, again, sort of this whole digitization and problem, just to do this, if you actually try to bang this out directly, again, it's going to be an n squared operation. That's going to get complicated as the number of your data samples go up pi. Okay, and data samples could literally be like, this could be, say, a couple minute song, and you're trying to, do 10,000 samples per second to catch all of the high frequencies. Like the human ears, our highest frequencies are, somewhere in like the 30,000 hertz. So actually 10,000 times per second would not be enough to catch the sort of high frequencies. You have to be sampling at like probably 100,000 times per second to truly catch some of that. Okay, so pretty high frequencies. That's actually why sometimes on like recordings or movies, it's not quite the same as real life sounds. Usually, Hollywood's gotten really good at kind of tricking us, especially on some of those higher frequencies. Okay, so that's anyways. This is an expensive operation, and there's a fast Fourier transform, or FFT, so that's different than a Fourier transform. So that's another thing I've heard a lot of people talk about. They'll say, "I have to go do the FFT." It's like, no, do the Fourier transform, but fast, absolutely. Okay, so actually, if you write out what this calculation is doing, there's this really cool. I'm gonna get it right. I think I wrote it down. I think Cooley. I didn't write it down. Darn. They realized that there was a pattern, and that actually, if they sort of calculated some things in a pattern, you could calculate it and then reassemble it. And basically, that algorithm is n log n. So, anyways, big deal. Okay, that really makes things fast. And so, again, back to the power of algorithms for solving things. And this is direct. Like, this is actually not. It's not a estimate. It's actually just taking advantage of the structure behind all of this. So, anyway, really cool algorithm. A very famous algorithm that many people have heard of, FFT. Okay. And then the third part I wanted to talk to you, because it's related, is actually on interpolation. Okay, so that's almost this thing back here where I'm saying, no, I have a data point, and I'm trying to estimate between the two data points, or I have a numerical algorithm I'm trying to estimate between the two. Okay, and so just like the wrong choice here can make this intractable, one of the most common ones is just fitting a straight line between the 2 points. Why? Because it's not just that it makes sense; it actually that you can solve it without having massive errors in your computational line that you don't know about. Right? The scariest thing we're doing in numerical analysis is you get an answer and you have no idea how big the error is. Okay, and so Lagrange interpolation. So if I have two data points here, okay, what in here between A and B, what a Lagrange interpolant is doing is actually saying I've got one function that goes from 0 to, this is f of b, as you go from A to B, and I have another function that goes from f of A down to 0 at B. Right? And so, let's see if we can write that down. That means f of x, okay? And that's going to look like x, so if x minus x2 over x1 minus x2 times f of x1, so that's A, and then plus x minus x1 over x2 minus x1 f of x2. Okay, so it's a very simple line, and so the kind of the combination of the two is going to give you a resultant that goes through like that, right? And so it's very fast. It's linear, and gives you good methods between. So again, all of these other curves, you've probably heard the word as well, called splines. Okay, and so yes, you can actually take a couple points and link them together in arcs. Okay, B-splines are one of the more common versions of that. And so just, anyways, the point is to be careful. You're always guaranteed to have a straight line between 2 points. That's why why this works. But you're always going to have jagged steps, and a lot of times, so B-splines, a lot of where that comes in, CGI. So you ever watched Shrek or something like that, like these surfaces, the B-splines will actually have the property, they might be linking 3 points together, but they're going to link them together such that the next 3 has a smooth, so that the tangent and the derivative is smooth between them. So there are lots of different properties. So if you're just going to do it for basic interpolation, just stick to linear, don't worry about it. And if you have to do something higher order, do dig into your data set, do dig into what's appropriate. Again, spline packages and stuff all going to be throughout MATLAB, all through Python, and not too hard to do. And I'll just leave you with one last warning, which is the non-extrapolation. Okay, and so even if you look at this kind of funny diagram that I did here, you might think this data point is going up and to the right. Okay? Generally, I try to draw the same curve I did here. Now, what happens if you take a straight line extrapolation? Well, you would actually extrapolate out this way. Okay, which is not the case. So be very, very careful on extrapolation. In other words, like basically don't do it, or make sure you're plotting it and you're making sure the extrapolation is okay. So if you just did first order linear extrapolation, you would extrapolate this one and it wouldn't make sense. You probably actually wanted to do is come back here, do a curve fit, and do an extrapolation. There are some times where I've done some curve fits and stuff where I think it's looking okay, but then actually for some reason it does that. And I'm extrapolating past some data set I have, and I'm getting like a negative number. I think, what's going on here, okay? So extrapolations are rife with error, so just write that kind of down as a danger. Extrapolations. And, there's nothing surprising here, right? We humans get in trouble too. Well, we call them predictions, right? If it's extrapolation past some known data points. But just know that numerically the computer, there's not really any good algorithms that are going to tell you how good the extrapolation is. We don't have that, right? There's nothing to compare against. There's no source of truth. And so usually what we mean from an extrapolation is actually the human is looking at the data. Maybe there's a world where we get our AIs trained up well enough. But what we're actually talking about is the human is looking at the data, and the human has an idea of where it should go. And then when we see something like this, the human is then using our own judgment saying, no, that doesn't look right. Let me come back and adjust it. Okay, so the computer, again, is just digital workhorse. Extrapolation is bound to be wrong. So be very, very, very careful there. And as always, dig through any of these. If this is more in the field that you're getting into, I'm barely even scratched the surface here on Fourier analysis. But for many people, this is the workhorse of what they do in engineering or science. And so just kind of some of the basics here on both curve fitting, Fourier series, Fourier transforms, and interpolating extrapolation. Okay, we'll see you next time.